Howdy, folks. Today we are going to talk about something near and dear to every science teacher's heart, which is the relationship between theories, hypotheses, and laws in science, and what those three words actually mean when we talk about them in a scientific context. I know this is near and dear to every science teacher's heart because I know every single one of us has at some point in our life, probably many times in our life, heard someone say, well, that's just a theory. And that's to the point that that very phrase was actually quoted and rebuked in some of the textbooks and reference material that I used in order to make this video. So we have all heard it. It annoys all of us, but it's because the word theory, when we use it colloquially in everyday speech, means something different than when we use it in science. And a big part of this stems from the fact that there's actually multiple different types of science. We often teach that science is just hypothesis science that relies on our scientific method to thoroughly test and advance our knowledge. And that is an extraordinarily important part of science, but it's not the only part. There's actually something called discovery science in academia. And discovery science is just going out and recording stuff, collecting data, observing the world around us, seeing what happens, and that actually produces a lot of useful raw data. On the other hand, hypothesis science is when we use deductive reasoning, when we use logic. We base off of our observances in the past, we try to predict what is going to happen in the future. But the hypothesis is not the prediction. The hypothesis is actually a proposed explanation of a given observation that we've made in the past. And then we can say, well, if this hypothesis is true, we predict that this event will happen. And that's what's testable, and that's what we are testing when we use the scientific method. So the hypothesis is just the proposed explanation, and then our prediction is whether what we're testing, if it's true or false. So like you could hypothesize that your phone isn't working because the battery is dead. So what do? Go plug it in. If it charges and starts working again, then yeah, your battery was dead. But if it doesn't, that means something else is wrong. Maybe the battery is dead, but something's wrong with the charge port. Maybe there's something with the circuitry going on in your phone. And that's actually something really important that happened just there that we kind of glanced over, because phone's dead is a fairly commonplace thing. A good hypothesis is actually really easy to disprove. And that's something that you can get from working with statistics, especially. If you can easily disprove a hypothesis, it means that if you prove the hypothesis is correct, or at least that it can correctly predict the future, because proving it truly correct takes a lot more data than just one experiment. But if you prove your hypothesis can predict the future, but it would be easy to disprove it if it did not predict the future, well, then you've got some really strong data to say there's something interesting going on here. And as I'm sure many of you have heard time and time again, when we say hypothesis, what we really mean is theory, colloquially. People use the word theory like we have a theory, or we had a theory back when I was in high school, that there were not any weapons of mass destruction in Iraq, and that Bush was making it up in order to have an excuse, a casus belli, to try and invade. That was just a hypothesis then. We looked at the data, we looked at what we were seeing on the news, and we made a hypothesis. Now, that hypothesis did turn out to be true. There were not weapons of mass destruction in Iraq. But that did not mean when we were making the hypothesis that we had a theory. Even though a lot of people thought that, and a lot of people probably did say, I have a theory there's no WMDs in Iraq. So, what is a theory then in science? It's not a hypothesis. A theory is made up of hypotheses that have been repeatedly confirmed and connected together. A hypothesis is often very narrow in scope, and while it's based off of previous experience, it might not have a lot of evidence backing up. It could, though. It could have a theory standing behind it, but especially if we're trying to break new ground in science, we're taking a logical leap and seeing if this hypothesis that we have does get backed up by the evidence. So when we get enough of those hypotheses being confirmed, we can synthesize it into a new theory. The hypotheses are very narrow and very specific, but theories are broad, they're big, they're all-encompassing. Well, maybe not all-encompassing, but they do cover vast swaths of territory. And they're able to explain lots of observations. They're able to explain lots of phenomena that we see, and usually they end up being pretty elegant ideas. So if you've got something elegant that explains a lot of things, you're probably sitting on a theory, especially if it's been confirmed repeated times. This is why theories don't just get shot down most of the time. If a theory like Newton's gravitational theory has evidence that contradicts it, most often scientists don't discard the theory outright. And there's a good reason for that, because oftentimes these theories allow us to make predictions. And if they allow us to make accurate predictions, there's some use to them. So most of the time scientists don't get rid of theories, they try to reconcile theories with any contradictory data. But if the data can't be reconciled, or if a new theory comes forward that can explain our observations in a more elegant way, such as we had between heliocentric and geocentric solar systems, Copernicus's theory that the Earth went around the sun, not the other way around, made the wandering orbits of the planets in the night sky. It explained them much more elegantly than the spheres within spheres of the old Ptolemaic system. That's when we can overturn a theory, when we have a new one that explains everything that's happening more elegantly, more easily than our previous theory, even after modifications. And the really important thing about theories is this is a groundwork. So we can use that to create more hypotheses. And we can constantly go back and forth and test the hypotheses and see it for ourselves. The advantage of this, though, the reason we want to have these big all-encompassing theories, is that science has become so specific at this point that it's very difficult, if not impossible, for any one scientist to confirm every single experiment that has been done by the long lineage of scientists that have came before them. So these theories allow us to build on that old metaphor of looking far because you're standing on the shoulders of giants. That allows us to do that. It allows us to stand on the shoulders of giants and get a firm foundation from which we work. Okay, then what are laws? Wouldn't that mean that laws are more solid than theories? And kind of yes, kind of no. A law in science is a very well understood phenomenon. They have lots of strong evidence, just like theories, but unlike theories, laws are very narrow in scope. They define a specific relationship, either verbally or, especially if you're working in chemistry and physics, mathematically. They describe a relationship between phenomenon, and oftentimes these are deterministic relationships, cause and effect. Like if you increase the volume of a gas's container, you will likely decrease the pressure if the temperature remains the same. Those three things are combined together in ideal gas law, P1 V1 over T1 equals P2 V2 over T2. So if you change one of them, the others have to change in response. It's deterministic. And that's why oftentimes these are mathematical, because we can put numbers onto them very easily. A law is often very short, it is often very easily expressed, and it's also often combined to a very specific set of conditions or assumptions. A common one that we teach in high school chemistry is ideal gas law. Ideal gas law doesn't actually work in the real world. Real gases do not behave the same way that we assume an ideal gas works. Why do we still teach that law? Why do we still use the law? Well, we teach it still partly as a scaffold to making the corrections that allow it to work with real gases, and partly because most of the time, real gases are under conditions that ideal gas law works for. They behave like ideal gases. So we can use the law while we are within the bounds of that specific set of conditions. And that law is then able to summarize vast amounts of data that we've collected through our observations and experiments over time. That is why we create these laws. But it's not just that someone gets to say, I have this law, I have this theory. That's why we have the peer review process. Scientists go through rigorous testing and examination before we're willing to adopt new laws and new theories. Scientists have to persuade one another and show their evidence and show their reasoning and rationale before those things are accepted by the general scientific community. So when we talk about these three words, the hypothesis is our prediction of how things are working. This is what we say, this is how we're explaining that we have an idea for how this system works, and these are the predictions we can make and then test out of it. A hypothesis is created, or a theory is created when you take a bunch of hypotheses and are able to explain them with an underlying framework, whereas a law is a very specific deterministic relationship we can describe between two or more phenomena. So these are the references that I used in order to make these videos. They are all very solid books. If you want to check them out, biology is one of the most widely used biotextbooks in universities. And if this is helpful, if you've appreciated, do those things that help the algorithm, like, comment, and subscribe. Let us know what types of videos you would like to see and what things that you want to learn about. We're also on Patreon and have a Facebook page if you want to stay up to date, and keep on learning.